It was requested last week that I go through momentum again and maybe just break down the fundamentals of momentum. And so this session may be just fundamental based, just going over certain rules, going over certain principles, probably loads and loads of examples that we'll go through just to solidify. And also you guys must obviously ask me questions where you guys are going wrong. Yeah, I can help you guys there. So that's what the session's going to go over. I'm going to try and draw it out in like a map for you guys. Okay. Right. So just to draw a little map for you of momentum quickly. Of course, we know the base formula is P, which is obviously for momentum, is equal to mass times the velocity of an object. All right. The unit that we measure momentum in is obviously kilograms per meters per second. That's the stuff we all know. All right. And we all know that it is a vector because momentum has direction, either forward, backwards, west, east, north, south, wherever, it has direction. Okay. Then we have the laws or principles of momentum. Okay. First one, the change in momentum. And then we have the other one, which is the conservation of momentum. Okay. With the change in momentum, we know that delta P for the change in momentum is equal to mass times the change in velocity, or more specifically, mvf brackets vf minus vi. All right. And we need to note very boldly that you must add a direction for the change in momentum, of course. That's a block on its own. This gives notion to another part, which is known as impulse, all right, which we know is the net force multiplied by time, or otherwise known as F net, times delta t. That is also equal to the change in momentum. So impulse can also equal the change in momentum. Well, this part can equal to the change in momentum. The unit, all right, will either be, depending on what you are given, newtons per second, which is obviously the force times delta t, newtons per second, or kilograms per meters per second. Right, conservation of momentum. Okay, maybe let's just finish everything on this side quickly. Then we have Newton's second law. In terms of delta P, sorry, the change of momentum, is that F net, obviously we know F net is equal to mass times the acceleration, but we know that acceleration is equal to the change of velocity over time. So you'll get F net is equal to, let me actually just show it from the beginning actually. We all know that F net is equal to mass times acceleration. We do know acceleration is equal to the change of velocity over the change in time. Right? What is m times the change of velocity? It's obviously this formula. So that will obviously give you this top part here. Will give you this part over here. Therefore, Newton's second law in terms of the change in momentum will give you F net is equal to the change in momentum divided by delta t. Then when it comes to the conservation of momentum, in collisions and explosions, okay, in an isolated system, right, momentum is only conserved in an isolated or closed systems, okay? The sigma, or the sum of the initial momentum, must equal to the sum of the final momentum. That is the base block there. Following that, we get two different types of collisions, namely elastic and inelastic. Inelastic is a bit easier, of course, because we know that EK, kinetic energy, is lost or there's a decrease in it. But when it comes to elastic collisions, all right, we know that the sum of the kinetic energy initially must equal the sum of the kinetic energy after or final. If those two are the same, if these two here are the same, we know that kinetic energy is conserved, it is not lost. We know the collision is indeed an elastic one. I just picked up I spelled impulse incorrectly. If there is a decrease in the kinetic energy, that means the collision is inelastic. Obviously, we want elastic collisions because we want to conserve everything. And that, ladies and gentlemen, is the entire momentum topic in a mind map. Okay, now before we move on to unpacking each section example by example, please do share if there's any questions, maybe that anything is not clear on this little map that I've drawn. All right, so what I want you guys to do, I'm going to have a look at the first question I'm going to have a look at from work just from bottom to start. I want to just have a look at the Newton's second law in terms of momentum. That way we also get to practice a bit of Newton's laws from grade 11. Also fix up any rusty parts there. So let's just go quickly with a little light example. Cool. Okay, so I'm going to give you a 5 kilogram model rocket. All right, 5 kilogram model rocket. Okay, that is launched from rest and reaches a velocity of 12 meters per second in 3 seconds. Okay. Number one, please calculate the change in momentum of the rocket. And then number two, please calculate the net force experienced by the rocket. Okay, so the first question they asked us to calculate the change in momentum. Change in momentum, okay, of the rocket that decided to launch. This is quite a basic one. Okay, so number one. Okay, obviously we know the change in momentum is given by delta P is equal to mvf minus vi. Okay, they said that the rocket was launched from rest, right, and then reaches a velocity of 12 meters per second in 3 seconds. Okay, and it's 5 kilograms, so for mass 5, vf 12, vi 0, there's a minus sign in between. Therefore, change in momentum should be given by 60 kilograms per meters per second upwards. Pretty basic. Right, number two, I'll turn this on. Oh no, side. And the second one was the net force experienced by the rocket. Okay, they'll be using the formula F net is equal to delta P divided by delta T. We've already calculated delta P already, so it's 60. We know the time was 3 seconds, as mentioned over there. 60 divided by 3, and that gives us an answer of 20 newtons, direction upwards. Any questions on
20,
those?
isn't it newtons per second?
But they asked me to calculate the net force, and net force is measured in force is always measured in newtons. If it was, for example, if net divided by delta t, then that is newtons per second.
Okay, thank you.
All right. Oh, as well as if net times delta t, there's also newtons per second, just in a different way. Cool. My pleasure. So for the second example, all right, I got a car of about 800 kilograms, quite a heavy car, and it moves east at 25 meters per second. A braking force is applied, and by the brakes, and that is FA, all right, as well as the frictional force, right, which is, let's find it looking F, increases the velocity of the, as well, and it decreases the velocity of the car to 10 meters per second within 6 seconds. Okay, 6 seconds. Okay, calculate. Number one, the same thing. Change in momentum. And number two, the net force on the car. Should take you less than 5 minutes. Go. Just to go through the first one again, remember the change in momentum we know is given by delta P is equal to mvf minus vi. We're well acquainted with this formula, of course. We know the mass of the car was 800. And we know the velocity, the final velocity was 10 meters per second because of the brake force that was applied to it. Initially, it was boosting at 25 meters per second. If we do the math there, we'll end up with a negative answer, negative 12,000 kilograms per meters per second. And our final answer, because we need to add a direction, will obviously be equal to 12,000 kilograms meters per second, and direction would obviously be west. That's what the negative told us. All right. Number two, they want to know the net force in terms, obviously, in terms of the change in momentum. First mark will go to your formula, of course, showing that you have arrived at the party, you're on the guest list. Now, this is where I know I'm going to get another question, so I'm just going to state this now while I'm at it. If I'm going to sub in the value, please keep in mind that this answer here is known as the value. This is the value of this, okay, which is negative 12,000, okay? This over here is stating my answer as a vector quantity, because that's what momentum is. It's a vector quantity. It has direction. Therefore, for the value of delta P, I cannot sub in 12,000 kilograms per meter per second west. I need to obviously sub in this value at negative 12,000, because I'm just looking for the value, right? Divided by the time that they gave me, which was 6 seconds. If I do that, I'm going to get a force or net force of negative 2,000 newtons. I cannot leave my answer as my value. I must put it in the vector quantity. Therefore, F net is equal to 2,000 newtons west. Right, for this question, during an investigation, a police officer fires a bullet with a mass of 15 grams into a stationary wooden block with a mass of 5 kilograms. That's my calculation incorrect. Suspended from a long, strong cord. The bullet remains stuck in the block, and the block bullet system swings to a height of 15 centimeters above the equilibrium position. One, I would like you to use energy principles to show that the magnitude of the velocity of the block bullet system is 1,71 meters per second immediately after the bullet has struck the block. So just looking at that, do you think you guys will be able to do that? Would you like me to go through that with you? So that's a new question. Let me just show you the drawing quickly. We just draw it first. Okay, so before you guys go back to the question, let me just take it back just to the screen quickly. So maybe you guys can just draw the picture. So here we got a bullet of mass 15 grams coming into a block of 5 kilograms that's suspended from this little string here. Once the bullet hits the wooden block, the cord then swings to a height of about 15 centimeters above the equilibrium position, which is this position over here. All right, this position over here. So that's the height is 15 centimeters. So we want you to use energy principles, all right, of mechanical energy. So mechanical energy at the top, mass equal mechanical energy at the bottom. All right, which we know we get two different types of mechanical energy. All right, we get two different types of mechanical energy. We get namely potential energy and kinetic energy. So the formula that you need to use, I'll just help you this far, is EP plus EK at the top is equal to EP plus EK at the bottom. We don't know what potential energy is. It's mass times gravity times height plus half mv squared, which is the formula for kinetic energy, which I'm sure we've all seen before. And then the same thing on the right-hand side. Okay, so just take that down quickly and then I'll switch screens. Just let me know when I can. You guys all got this down on the blackboard quickly, like you got this little part down and you understand the drawing. I can switch back to the question.
JP?
I'm here.
Would you have to work out velocity?
You would have to, yes. Because when I go back to the question, that's what the question's asking. I'll go back to the question now, as soon as Fozels is done. All right, so we need to prove via energy principles that this velocity is indeed equal to 1.7 meters per second. That is the answer. We just need to prove it. So we're doing a bit of a proof calculation here. That's all. Let's just go through the question again. ME at the top versus ME at the bottom. Okay. The H here in MGH stands for height. Okay, as you can see, the top part, this is definitely going to be the top. Why? Because the block bullet system swings to a height. Okay, this is the height of 15 centimeters. So this is definitely going to be the top. All right, because it swings above the equilibrium line. If something's at equilibrium, it's neutral. It's zero. It's stable. Okay, at the bottom would obviously be where there's no height. Because why? It's at the bottom. So this would be the bottom. Visually, I can see that. Now, to carry on using the energy principles for the question, we need to obviously prove that V is indeed equal to 1.71 meters per second. How we go about doing this is that we realize that at the top here, we've got potential energy. All right, we have mass times gravity times height. We have no kinetic energy at the top because once it gets there, it shuts down. It's nothing. Okay, so that will give us 0. So we're left with just MGH on the left-hand side at the top. Then at the bottom, obviously this has to swing back, correct? Because it doesn't have any hovering skills. Right? It has to swing back. If it swings back down to the bottom, the height of 15 centimeters now comes back down to 0, means we'll have no potential energy and only kinetic energy, which is half mv squared. Do we see what is this? M for mass, right? Right?
Yeah.
Good. And we also see M for mass on this side, right?
Yeah.
So we can get rid of them because they're the same thing. So divide by M, divide by M. I'm left with only GH is equal to half V squared. I want to get rid of this little half, so I'm going to multiply by 2 to get rid of the half. Everybody, I'm sure everybody knows how to do an equation by now. What I do to the one side, I do to the other. So I'm left with V squared is equal to 2 times gravity times height. To simplify that even more, I'm going to square root both sides. I'm going to carry on over here. Therefore, velocity should equal to the square root of 2 times gravity times height. And now I can do my subbing in. So square root of 2 times 9,8, because that's gravity, times height, which is it's 15 centimeters. I need to convert it to meters. So that'll be 0,15, because there's 100 centimeters in 1 meter. If I do that, and I do that correctly, I'll get a value of velocity should indeed equal 1,71 meters per second. And that's how you do it using energy principles.
How did you know what to
Wait,
cancel out in the beginning?
1,71.
That's correct. Sorry, yeah, to answer Christian's short question, it's 1,71 meters per second. And Fozia, you asked me, how did I know what?
No, I didn't ask you anything.
It's me.
Oh, sorry, I can't see your faces. Sorry, I can just hear voices. Sorry. Yes, Jesse?
How do you know what to cancel in the beginning? How did you know to cross out the kinetic energy on one side and the potential energy on the other side?
Okay, I looked at the sketch. First step I did was obviously recognizing which part was the top and which part was the bottom. The right hand side was most easy, because if anything swings back down to the bottom, if anything's at the bottom, it means there's no height. It's zero. It's at the bottom. Okay.
Okay,
So,
yeah, I get that one.
that's why I knew there was only kinetic energy left on the right hand side. Okay. Then on the left hand side, at the top, anything to have a height, I knew there was going to be potential energy. But for a brief moment, once it's suspended at a certain height, it only has potential energy and no kinetic energy, because even there it stops. So in other words, velocity will come to zero momentarily. When velocity comes to zero, the entire kinetic energy formula will give you zero. Hence, you only have potential energy. It's like holding a tennis ball, even when we're talking about vertical projectile motion, holding a tennis ball from a certain height, maybe it's you standing on top of your car, on top of a bakkie, on top of your building, whatever. The tennis ball itself has potential energy because it's suspended from a height of however many meters. Once you let that thing go, right, the height starts to decrease, okay? Its potential energy then gets converted into kinetic energy. Why? Because the object is moving. So once it starts moving, it starts dropping, obviously your potential energy gives zero, kinetic energy will equal some. Everybody understand? Any other question?
No, if it's at the bottom, then isn't it not moving?
Yeah, something's at the bottom, yes. Okay, why?
Then why do you leave kinetic energy there?
Because in order for it to go from the height of 15 centimeters back down to the bottom, kinetic energy had to have been exchanged.
But then why is there no kinetic energy on top if it moves from the bottom to the
Because
top?
while it's at the top, there's no kinetic energy. While it is at the top.
Are we looking at this brief moment when it's just like at the top? We're not looking at the whole thing when it comes back down.
You're not looking. For the potential energy, you're not looking at the whole thing when it comes back down. When it comes back down, you are only looking at kinetic energy.
So we're looking at when this thing is just like in the air, just that one moment.
Yeah. So
Okay.
we're not looking at the chip from when it was at the bottom to the top. We're looking at the chip from the top to the bottom.
Say it again.
Yes, I'm
Thank you.
listening. Welcome. Yes.
For the top of the for the top part now, that
For the
must
top
not be when the bullet system block thing is in the air together. The bullet is in the block, right?
Mm-hmm.
So would you not have to add the masses?
Okay, that's what you're asking. The nature of this question doesn't require us to do that. No.
But if the nature of the question did require us to do that,
Then yes, you would.
When would it do that?
Well, they would ask you they would ask you in another question. Maybe they would have asked you a momentum question prior, where you would have had to have added the mass in. Maybe they would have asked you initial versus final momentum. So sigma initial, so the conservation of momentum. Then you would have had to have done that, or for change in momentum. But in this case, they just asked you to calculate the velocity, and all we do is just focusing on the question at hand, not trying to do anything more or anything less. So we didn't have to add any masses to the equation at all. Could just get rid of them.
Is that why you divided by m to
Yes,
get the okay?
that's why. The next question is indeed a conservation of momentum question. And let me just get that question for you. Everybody see the second question? Second question is calculate the magnitude of the velocity of the bullet just before it strikes the block. We calculated previously the velocity after it struck the block. We want to know the velocity of the bullet just before it strikes the block. This is, as I mentioned, a change in momentum, the conservation of momentum question. So I'm giving you guys a little bit of a hint to what type of question it is. Anyway, okay, so the question again, calculate the magnitude of the velocity of the bullet just before it strikes the block. In the previous question, we calculated what it was after it struck the block. So we calculated that velocity already in the previous question. We are looking for this bad boy over here. All right? We want the velocity of the bullet, which is BU for bullet and BL for block. Okay? Understand something, this part here, let's just focus our attention here quickly, that this is the mass of the block times the initial velocity of the block. We know that the block was suspended from a strong cord. It was just hanging there. The block was not moving. So this was equal to 0, hence making this entire MBL times VIBL equal to 0. All right? That's pretty much basic to understand because it was not moving. Hence, the entire system of the mass of the block times the velocity of the block is equal to 0. There's no momentum there of the block itself. There is, however, momentum of the bullet, right? We knew that the bullet was 15 grams. If we convert that, it'll be 0.015 kilograms times VI, and I'm still going to say VIBU. Okay, so that's our unknown. We know the mass of the bullet was 0.015. We know the mass of the block was 5 kilograms. So it's obviously going to be 5.015 times 1.71, which we just calculated. All right, so that's going to be 5.015 multiplied by 1.71, and that's going to be 0.015 VI BU, the initial velocity of the bullet. Okay, we're looking for this bad boy on its own, so we get rid of the 0.015 on the side, and we divide 5.015 times 1.71 divided by 0.015. Therefore, we should get the velocity of the bullet before it strikes the block to equal, if I sub in on my calculator, which I am using, 5.015 times 1.71, all divided by 0.015. The final answer there should be 571.71 meters per second, which is accurate because a bullet can travel very fast. I got a question, yes?
Can you explain why it's plus 0?
This one here?
Yeah.
Okay. Cool. So the reason why this whole mass of the block times VI of the block is equal to 0 is because we know that the mass of the block was equal to 5 kilograms, correct? We're happy with that part. Okay. But in terms of the block itself, the block, when it was suspended from the cord, okay, I'll just draw the block. All right, it was stationary. All right. The bullet was entering the block over here on this side. The bullet had a momentum because it had a mass and it had a velocity. The block itself was stationary. So if VI of the block is equal to 0, 5 times 0 equals 0.
Oh.
Hence why I just made everything 0. Instead of doing the whole 5 times 0 equals 0, I just made everything 0 because I knew that there was no velocity of the block when it was hanging from the cord before the bullet struck it, because that's what we're calculating, the velocity of the before. We have another 10 minutes. Do we have time for one more?
Yes.
Yes, we do. Lovely. Seconds. All right, that's the third question. Should take us about 5 minutes to do. Does everybody have the question down or they know what the question is asking? I'm going to switch back to the blackboard just to show you guys one thing quickly. And then I'll switch back to the question if no one has it.
Yeah, you can switch it to Blackboard.
Okay, I'll switch to Blackboard quickly. Remember, this question now, we are asking again for the force on the bullet. Okay, we want the net force that's on the bullet, okay, which is obviously going to be given by the net force is equal to the change in momentum that we're concerned with the bullet, okay, divided by time, or delta t, okay, it's this
What
form.
was time?
0.2 seconds. Okay, we obviously know the VI of the bullet was equal to 571.71 meters per second. And, you know, the final velocity of the bullet was 1.71 meters per second. And we also know that delta t was equal to 0.2 seconds. And we know what the change in momentum, the formula is given by mvf minus vi. Okay, we've got about 2 minutes left of the session because it's supposed to end at 7. So I'm going to go ahead and just get started on helping you with the question. So carry on. You're still busy. I'll catch up with you, or you'll catch up with me. So to further expand this part here of the formula, we know that, like I mentioned, the change in momentum is given by this equation. So I'm going to go and expand that. Vf of the bullet minus Vi of the bullet, all multiplied by the mass, all divided by delta t. I know that the mass of the bullet was given by 0.015 multiplied by 1.71 minus 571.71. All of that divided by 0.2. And to simplify, I have 0.015 multiplied by negative 570, right? Because 1.71 minus 571.71 gives you negative 570. The same way if you had to take 571 minus 1.71, you get positive 170. This is obviously just the reverse. all divided by 0.2. You pop that in your calculator. 0.015 multiplied by negative 570, all divided by 0.2, gives you an answer of negative 42.75. All right, and the final answer would obviously be 42.75 newtons. And we obviously need to give the direction, right? Because remember of the bullet, in which direction was the bullet going?
East.
East.
There you go. It's going towards the block, right? So
So to
42.75.
west.
No, it will definitely
So be west. Oh wait, but
The reason why we got a negative answer,
confused.
the reason why we got a negative answer, I'm going to explain this quickly, and I knew I was going to get this question. It's good. I'm not upset about it. The reason why I'm going to explain this question is that, remember, we are dealing with the bullet itself. We are not dealing with the block bullet system. Okay? Right? We are only finding out the force of the bullet on the block. That's all we're finding out. We're doing nothing fancy. Okay? I'll read that question again. Calculate the magnitude of the force that the bullet exerts on the block if the impact only lasted for 0.2 seconds. Unfortunately, we got a negative because the block bullet system, or the final velocity of the bullet when it was in the block, slowed down by 570 meters per second.
Can
Can we see that? Yes?
So they took east as negative
It's got nothing to do
because of the
necessarily.
negative answer.
It's got nothing to do with that necessarily. I'm explaining why it would the force of the bullet will still be going in the same direction as the bullet. I'm explaining that quickly. The only reason why that is because, remember, the final velocity of the bullet in the block was 1.71. All right. Usually, it would have, if any object's final would usually, if it was still going in the same direction, would have been a positive answer. So maybe this would have been over 571.71. Because it got stopped in the bullet, it got slowed down by 570 meters per second. But yet the force of the bullet on the block still exerted a force of 42.75 newtons. And which way was the bullet going initially?
East.
Exactly. So the force of the bullet still exerted a 42.75 newton force, 42.75 newtons on the block. In terms of the block bullet system, all right, the net force of the block bullet system, this would be west.
But they don't say it's also coming down, so it will remain east.
Yes. Like I say, we get the negative answer because the F net of the bullet inside the block would be negative 42.75 newtons, west. But the bullet itself, the force that the bullet exerts on the block is 42.75 newtons east. The only way you can get that right is if you comprehend that the bullet was going towards the block in an easterly direction. The block doesn't exert a force on the bullet in this case. We're still confused.
Nope.
Okay, Fozzy is fine, but is anyone else still confused? Speak now. You can stay a bit longer.
What's the difference?
It's the difference. That's a good question. So the F net of the bullet, remember I wrote from the beginning on top here, we just want to know the bullet. We're just looking for the F, the force on the bullet. We're not looking for anything else. Okay? The net force, okay, of the system would be negative 42.75. But the force, the F net of the bullet on the block is 42.75 newtons east or to the right. Because the block ended up from here, the block ended up there. at a height of 15 centimeters above. So here the bullet is inside the block. Here the bullet must still enter the block.
Nope. Makes sense.
Glad. Who does it not make sense to? Please, this is a safe place. If everyone's happy, I will end the session. If everyone is happy, if no one's happy, please do stick around. I have time. I take it everyone is happy.
Yep.
Fantastic.
Yep.
Right. If everyone's happy, thank you so much.